So these are pretty much personal definitions. And I'm sure somebody's going to take issue with some parts of them, but we'll give it a shot. So first of all, occasionally we will talk about processors or processor packages. Pretty much what we mean there is whatever goes into the processor socket. So the motherboard on your computer has a place where you put the actual part that makes it a computer, and the package or the processor package is what fits into that socket. Why this makes a difference is because we have some sub-definitions, one of which being core. Core, as I'm going to define it, is basically the logic and associated memory cache and things like that that are needed to fully execute a set of instructions, to load them, to actually do the work, and then store the end result. Now, dual or multi-core is a case where you have more than one core piece of thing that does work in a single processor package. There's a legacy term that has been used forever, CPU. It used to have a good term. It used to mean something sensible in the olden days. Pretty much it was a big box of iron sitting in a huge air-conditioned room. CPU nowadays is fully overloaded. It's really hard to know what it means. It's not very precise. I mean, it could mean core. It could mean all of the cores in a package. It could mean however many cores and packages are part of your system. Some people even use it to refer to the computer itself. It's not a great term, but it's bandied about. Processor or physical processor. What I'm going to use is the definition of it's either a core, it's overloaded again, it's either a core, it's all the cores in a package, or it's all the packages in a system. Again, not a very good term. In the past, you've probably also heard the term logical processor. This is the idea that when you look at a single core executing a program, what many times happens is only parts of the core are active at a time. You may be running a program which is doing multiplications, but it's not doing additions or shifts or not doing loads and stores or something like that. So part of any given thread of execution, part of it is inactive, and part of the core is inactive and part is active. So the idea of logical processors, and this is where the term hyperthreading, is Intel's term for it, comes around, is let's throw multiple threads of execution through the same processor, through the same core. When you do that, the theory is that much of the time, these different threads are going to be executing slightly different pieces of code. One may be doing an addition, one may be doing a multiply. The point is now you have two parts of the core, which is a very expensive piece of silicon, working at once as opposed to only one, and you get more work out of the system. It's not like dual core or multi-core where you have the full processing infrastructure duplicated, but it gives you, 5, 15, 20% better performance than just having a single thread of execution going through a single core. It can help. Another term you hear a lot in parallel computing, and when we're talking about multi-core or multi-threading, is concurrency. Concurrency is basically computing in which multiple tasks are active at the same time. And there are many ways you can use this. One of them is to hide latency from things like I/O processors, graphics, talking to the disk. It can be used to provide redundancy. If some systems have multiple processors that operate in lockstep. If one dies, the other is still there. You have this on things like the space shuttle and the space missions a lot. We really like to have redundancy. And then the third term, sort of place you hear about concurrency, is parallel computing. And parallel computing, what we're talking about here is using concurrency to decrease program runtime. The whole idea is you take a problem, you divide it into subtasks, and you try to execute those simultaneously on one or more processors. And that's pretty much the whole thing behind these multi-core processors. You want to be able to you use parallel computing to solve problems more quickly. In terms of parallel computing, there are subtypes. Throughput parallel computing is basically the idea is where you want the aggregate performance to be better than if you had a single machine running. The easiest example of this is something like a batch queue. You've got a gazillion machines, you have a batch queue, you submit 1,000 jobs to the batch queue, and the batch queue divides up the work amongst however many machines you have, and the more machines you throw into the system, the better throughput you get, the sooner it takes for those 1,000 jobs to finish. And that is a very valid form of parallelism. It's used a lot. The other is latency-sensitive parallel computing. This is the idea of I have a job, running a spell check, doing a financial calculation. I want it to finish in a faster time. I want a faster turnaround. And this is where we talk about multi-threading or sometimes message passing. We'll get to in a second. That is where these sorts of things are used. So latency-sensitive parallel computing, we want to shrink the overall runtime of a single job. Multi-threading is basically how we do latency-sensitive parallel computing using a single process. We divide the address space and all the infrastructure, which allows a single process to run on a computer, a process being something like Outlook or Internet Explorer, or choose your program of choice. And you basically have that process doing multiple things at once as a single process. The whole idea here is that these multiple threads as execution make use of shared memory. And shared memory allows the threads to pass data between each other, but it also introduces pitfalls, such basically you have to worry about how do you synchronize who writes to a given part of shared memory. And then the final term I'd like to discuss quickly is just message passing. This is the idea where you implement parallel programming without shared memory. And pretty much this is implemented as separate processes which, again, work on a single task in parallel and try to finish it in a shorter period of time. But instead of using shared memory and existing in the same process, they're separate processes. And occasionally they chat between each other or use some sort of shared memory in the system itself, which is outside of process space to do things. Databases would possibly be a good example of message passing, where some implementations do everything within a single process, which they're basically a multi-threaded implementation. Other implementations, they have multiple processes handling various network users, background tasks like logging and things like that, happening in multiple processes, and they communicate between each other using various messages.